Hello and good afternoon. My name is Sayan Mitra, and I'm a professor at the University of Illinois at Urbana-Champaign. And I'm going to talk about our project on continuous assurance for autonomy software. Systems powered by AI and machine learning present us with tremendous opportunities to solve some of the biggest societal challenges, from transportation to the impacts of climate change, sustainable energy agriculture, all the way to healthcare and home care for an aging population. To reach this potential for autonomy, we also realize that we have to address the challenges of safety, reliability, biases, fairness. Explored how formal verification technologies could enhance the reliability and safety of autonomous systems. This slide shows the overall ecosystem or the workflow that goes into developing, testing, and certifying an autonomous system. So on the left-hand side here, we have the core artifacts that go into building an autonomous systems like code, data, models of the environment, rules, and also the specifications that define the kind of product that we are trying to build. Then in the center here, we have the testing and verification engines, which can include a number of different kinds of tools and frameworks. But ultimately, out of all this, we expect to be able to generate a certificate or a proof that provides compelling evidence that the system indeed satisfies the requirements under a set of environmental conditions or assumptions. So these are the certificates that would ultimately go into building public trust, as well as satisfying the certification needs for the regulatory bodies. Also, one of the outcomes of this testing and verification pipeline would be counterexamples or bugs that illustrate where, under what conditions, the system violates the requirements. And this can be super useful for improving the design, guiding the collection of more data, as well as to understand some of the machine learning models, which may be black boxes. Now, one of the key factors in making autonomous systems more resilient and safe in the face of adversarial changes, dynamic changes in the environment, is how quickly this loop can be closed. So in this project, we started by studying the state of adoption of formal testing in the software industry. And then we took stock of what has been happening in the space of verification, validation for autonomous systems, also called cyber physical systems. And then we tried to understand how to integrate some of the existing techniques into a continuous testing and reasoning pipeline, and also identify some of the challenges that we see are going to be important for further adoption and scalability of formal techniques. So the lessons, one of the lessons is that the verification toolchain must communicate with the developers using the artifacts and APIs that are already part of the workflow. Trying to invent a new language or a formalism that has to be learned first and then has to be worked into a pre-existing workflow proves to be extremely challenging. Also, autonomous systems where there is a heterogeneous set of different tools and languages that are in use. And there has been a bias towards creating new languages and logics for verification thus far. Now, switching on to the kind of verification validation that has been happening in the cyber physical system world, one of the major successes over the recent years has been this idea of data-driven verification, where simulation data is used together with whatever knowledge is available about the models of the system or the code, and combine these two things together to develop certificates of correctness. So for example, in this recent ITSC paper, we show how formal verification techniques together with this data-driven approach can be used to analyze. There is also applications of these techniques to controllers, control systems. As a part of this project, we developed a pipeline for continuous testing of autonomy software. This was developed in the context of an autonomous vehicle racing competition that we ran as a part of CPS Week in 2021. There's going to be another iteration of this competition in 2022. So competitors in this race competition submitted code for controlling an autonomous car, and our testing pipeline would then embed this code inside a simulator, spin up different tracks and simulation environments with pedestrians and other vehicles, and then do a thorough testing of the submitted controller code and produce a score. This whole thing was developed using a number of software tools that are available, like Docker and Jenkins and AWS Lambda, and it was entirely automated. We could scale it up to, in parallel, test a number of different vehicles on different tracks. So what we learned from this exercise of setting up this continuous integration pipeline for autonomous systems is that indeed fairly straightforward to create this continuous testing pipeline, even though autonomy software has to be closed within a simulation environment to do the end-to-end testing. It's not adequate to test individual units or modules. You have to put together the entire autonomy pipeline and then embed that pipeline inside the simulator, which brings with it several challenges. For example, non-determinism is a significant challenge in testing and validation of autonomy software. We found that non-determinism mainly arises from the communication between the different modules. For example, in an autonomous car, you have a camera system which is talking to a planner, which in turn controls the actuators in the vehicle. And between each of these, there are different communication protocols, for example, ROS or Mavlinks. And some of these protocols do not come with hard real-time guarantees or time bounds. And this leads to an explosion in the uncertainty that the analysis has to deal with, and also exposes new attack surfaces. Secondly, the perception system in an autonomous vehicle brings with it its own set of challenges. These are built using neural networks, which are difficult to specify and test. And there are many different challenges for addressing an end-to-end system which uses a neural network. So one of the things that we are doing right now going forward is to scale up our verification and testing pipeline. And the fundamental idea that we are exploiting is the notion of symmetries. So although many of these software tools and models that we are using are complex, but because we are dealing with vehicle systems, we know that they satisfy certain underlying geometric properties and certain symmetries. And we are exploring how the knowledge of these symmetries, even in the cases where we do not have full information about the model, can be exploited to make verification faster or even testing faster. This is a line of work being pursued by Hussein Sibai, who's a recent PhD graduate from my group, and you can look at his publications. And going forward, we are trying to incorporate those ideas into the testing pipeline. The second direction that we are pursuing, and this is much more recent work by Chao, Shea, and others, is to abstract the perception modules with software or code that is more intelligible, understandable, and therefore easier to analyze, perhaps even tractable using existing formal verification techniques. Testing validation of autonomous systems in dynamic environments requires continuous integration to make the testing validation a part of the designer's workflow. And it is reasonably straightforward to create these continuous reasoning pipelines. But once we have the basic infrastructure, there are some deep technical challenges that we need to address in the form of non-determinism, scalability, and handling of perception modules, which use, in particular, deep neural networks.